Okay, so let me just write again the generalized Clausius inequality like this. This was always smaller or equal than the actual change in entropy, equal only if the infinitesimal process is reversible. Okay, so now let's think what happens if you have a system. Yes, if you have a system which is adiabatically insulated. Okay, so let's just put an adiabatic insulation around a system so it cannot exchange any heat with the surroundings. We're also going to make it mechanically insulated so that there's also no work being exchanged with the surroundings. So in this case, well, actually that's not necessary, just adiabatically insulated. So if this is the case, then the Q is always going to be equal to 0 because there's no heat being exchanged with the outside. So the entropy, infinitesimal entropy changes are always positive, or at the very least they are 0, but they can never be negative. Okay, and this has some important consequences. Okay, so if you think about it, if you have a system which is insulated adiabatically, you can never run any process that will reduce its entropy. Okay, so if you do an adiabatic process between any equilibrium state A and B, if this process is possible, it must be the case that S of B is larger or equal than S of A. Okay. So this tells you that there are many processes that are not possible. Okay, because you would need to reduce the entropy. If you want to insist in making them adiabatically, they are simply not allowed by the second law of thermodynamics. If you want to reach a state B, which has a lower entropy than your starting point A, then you necessarily must couple your system to the surroundings so that you can exchange heat with the surroundings and get rid of some entropy. Otherwise, you only generate entropy, or you keep the entropy that you have, but you cannot get rid of it while being adiabatically insulated. Okay, so this was actually something we had already said before. Okay, so if you remember, there was at some point when we were making remarks about the definition of internal energy. So remember internal energy difference between final state B and initial state A, and this is equal to the work done to take the system from the initial state to the final state along any arbitrary adiabatic process that you like. Okay, so what we said is that sometimes it might not be possible to connect a given state A with a given state B adiabatically. Okay, and now we see why this is the case. Okay, so whenever the entropy of the final state is smaller than the entropy of the initial state, it is simply not possible to run that process while being adiabatically insulated. Now remember that we still can define the internal energy difference between such states simply by running the process in reverse. Okay, so what we're going to do is we're going to go the other way from B to A. This is actually allowed because B has less entropy than A, and we're going to flip the sign. Okay, so this was the way that we surmounted this difficulty in defining the entropy, the energy difference between two states that cannot be connected adiabatically. Okay, so another thing, and this is more terminology. So in particular, whenever you have a process in which the entropy doesn't change, an adiabatic process in which the entropy doesn't change, this means that the adiabatic process in question is reversible. Okay, so when you have adiabatic plus reversible, because of the generalized Clausius inequality, what you get is no change in entropy. And no change in entropy, put in words, means isentropic. Let me see if I can spell it properly. Isentropic. Okay, so an isentropic process is an adiabatic reversible process. And remember that when you are thinking about an adiabatic process, reversible means quasi-static. All quasi-static adiabatic processes are reversible. Static. Okay, so that's just terminology. for instance, when you are running an ideal engine cycle like the Carnot cycle or the Otto cycle when you have adiabats, when you do these adiabatic processes reversibly, the entropy of the working substance of your engine or your refrigerator remains constant. Okay, this is sometimes useful to solve problems and to calculate things, so keep that in mind. Okay, so then let me talk about the additivity of entropy. That's just a side remark, just to make things complete. In this case, think about the system which is made of different parts. Okay, these parts can be, real, physically separated parts, or maybe it's an imaginary division that I make. So in this case, I'm going to think about a global system sigma that has 4 units: sigma 1, sigma 2, sigma 3, and sigma 4. Okay, and I want to try to make sense of the entropy of each individual piece of my system. So what is it that I need for entropy to make sense at the subsystem level? Well, first of all, if you do any process to your system and the energy changes in any amount, delta U, so you take the total system and you run a process and you calculate the change in internal energy by looking at the adiabatic work. Well, what needs to happen is that when you look individually at the parts of your system, sigma 1, sigma 2, sigma 3, sigma 4, the changes in energy of the subsystems must be approximately, at least, equal to the total energy change. It may be the case that some energy that is fed into the global system goes in strengthening or weakening the interactions that there may exist between the parts of the system, but we have to assume that these interactions are very small compared with other energy scales of the problem. So these parts of the system, if you like, are very weakly interacting with one another. If this is the case, then I can approximate the total energy change by the change in energy of each of the subsystems. And in particular, if I do some transformation, some mechanical, say, compression in the system, I inject a certain amount of work into the system. So if I can identify the total work injected in the system by at least approximately the sum of the mechanical work made on each individual subsystem, by maybe squeezing them, each of them a bit. If you look at what is the work that I have done in each of the subsystems, you add them up. If this roughly coincides with the total work that you actually applied externally, then what you can do is to use the first law of thermodynamics. So remember this, this I don't call delta, let's call it W only. So the total change in energy, by definition, is the work plus the heat. Okay, and what I'm saying is that the heat then equals the work, the internal energy change minus the work, and I say that I can write these things approximately, at least, like that in my composite system. So the total energy change is going to be the sum of the individual energy changes, and then I subtract the individual works that I do in each of the pieces. And this is my definition, this is a definition of the heat absorbed by each subsystem in my composite system. And once I know the heat, I can define the entropy in this way. I would say that the entropy absorbed by each part is going to be equal to the heat absorbed by each part divided by the temperature of the source from which heat is coming. Okay, and this is again a definition. So I define this is a definition for the local entropy, and because of all the assumptions I made before, the total entropy, which is actually well unambiguously defined like that, is going to be equal to, let's put this delta here, is going to be equal to the sum of the individual entropies, which is the sum of this delta Q I divided by T. Okay, so that's just a way to make sense of entropy of a subsystem. The key point here you have to remember is that subsystems couple weakly, then you can locally define heat You can locally define heat from local work and from local energy changes. If the interactions between the subsystems are large, then there will be a non-negligible amount of energy that can go to strengthen or weaken the interactions between the parts. Okay? Good. So finally, really extremely important point is the maximum entropy principle. And you are going to see why this is so important when we study the thermodynamic potentials chapter, because we are going to be using this all the time to calculate everything. Okay, so again, the maximum entropy principle is a direct consequence of Clausius' theorem, and if you like, also of the second law of thermodynamics. And it just, I quote, it says the most stable state of an isolated system is the state of maximum entropy. Okay, so when I mean an isolated system, what I mean is that the energy of the system is constant. Okay, so in particular, I don't make any work on my system. I don't inject any heat into it, so it's mechanically and thermally insulated. And this just follows from, once again, this generalized Clausius inequality in an insulated system like this. Okay, so imagine that I am, let's say, in an expansive system like this, and this is a volume, this is pressure, and this state here, okay, state A, is such, I know this, is such that the entropy is the largest possible. So any other state that I can visit will have smaller entropy. So this is the maximum, is maximal, let's say, in A. Okay, so then I say that this state A is stable. Okay, so what do I mean? Well, imagine that for some reason there is a perturbation, there is a small fluctuation, and my system will visit a neighboring state. Let's call it, A prime. Because of what I just said, the entropy of this other state A prime is going to be smaller than the entropy of A, because I said that this entropy is maximal. Okay, and the second law of thermodynamics just makes this process impossible, because we said that U is constant and I have an insulated system, so I cannot reduce the entropy. So if at some point I hit this state of maximum entropy, I am trapped in that state so long as the energy remains constant. Okay, so this is why the maximum entropy states are the most stable states of an isolated or insulated system. Okay, so this is something to keep in mind, because we are going to be using this a lot. And let me just write the name: maximum entropy principle. Okay, maximum entropy. Okay, so now we're going to move on to see a practical application of the concept of entropy.